students, so welcome back to 60 out of 60 in KCET Chemistry 2025 series in just 200 days. So today we'll be doing chemical bonding and molecular structure part 2, where we are going to discuss the most important topic, that is VSEPR theory, Valence Bond theory and hybridization. Okay, so this is the major part of the chapter from where you can easily expect questions. So please watch this complete video with full focus, with full attention, and note down all the important points that we are going to discuss. Okay, so next you can join our WhatsApp channel, link is there in the description section, so you'll be getting all updates, notes, PDF, everything in the WhatsApp channel. Okay, so yes, now let's get started. So today, as I told you, it is part 2 of this video, of this lecture, where we are going to cover VSEPR theory, VBT and hybridization. Okay, and in next class we'll be doing these topics. So weightage, you can easily see 1, 2. So weightage, you can expect 1 to 2 questions very easily every year. So today is part 2, and today we are going to discuss VSEPR theory, Valence Bond theory and hybridization, as I already told you. So in VSEPR theory, we are going to discuss exactly what is VSEPR theory and different shapes and molecules, geometry of the different molecules we will discuss. Next, coming to Valence Bond theory, we will be discussing about the orbital overlap concept. What is this concept we'll be talking about? Then overlapping of atomic orbitals. Then we'll be talking about types of overlapping, and then strength of sigma and pi bonds. Okay, next in hybridization, we'll be discussing about definition of hybridization, types of hybridization, and hybridization including d orbitals. Okay, so these are the topics that we are going to cover today. So let us start with the first one, that is VSEPR theory. So VSEPR theory tells you about the shape or the geometry of the molecule. Okay, so VSEPR theory says that the different bond pairs, lone pairs that is present in a molecule adjust themselves in such a way to minimize the repulsion. Okay, so the order of repulsions are lone pair is having maximum repulsion, then lone pair, and then bond pair. Okay, now another thing, a molecule consisting of only bond pairs form the basic structure. Okay, when lone pairs are introduced into the basic structure, they squeeze the bond pairs closer together. As a result, the shape is distorted and the bond angles are reduced. Okay, so I'll just tell one example here. If you see CH4, okay, CH4 is like this. Okay, and its bond angle here is 109 degree. Okay, now if you replace this with one lone pair, so suppose NH3 is also very similar to this, and you replace this with lone pair. Now what happens, there is lone pair and bond pair repulsion. Due to this repulsion, what happens, this hydrogen comes here. Okay, and this bond angle decreases to 107 degree. Okay, so that is about VSEPR theory. So now we'll be first talking about the basic structure, means there is no lone pair, only bond pairs. Then what are the geometries that is possible? So first of all, if you have number of electron pairs is 2, means 2 electron pairs are there. Okay, then the arrangement only possible is linear geometry. Okay, so you can see A, and this side, 2 side, there will be atoms, so that is linear geometry. Example, you can see BAB, and real life or real molecules, you can see BeCl2 or HgCl2. Now second one is your with 3 bond pairs. Okay, only bond pairs, no lone pair. Again, if you have 3 bond pairs, then the geometry here is called as trigonal planar. You can see this shape, bond angle is 120 degree. Example is BF3, or you can even add BCl3. Okay, next, if you see fourth one, if there are 4 electron pairs, okay, 4 bonds are there, then they arrange themselves in tetrahedral geometry. Bond angle here is 109.5 degree. Okay, and the examples here are CH4 and NH4 plus. Okay, so remember, for 2 it is linear, for 3 trigonal planar, for 4 it is tetrahedral. Now if we see 5 electron pairs, then the shape is trigonal bipyramidal. Okay, trigonal bipyramidal, you can see there will be one triangle, and then 2 sides there will be 2 B. So 3 B's are in one plane, and 4th and 5th B are on the upper and the lower plane. Okay, now here trigonal pyramidal example is PCl5. Now if you consider 6 electron pairs. Okay, then we have a shape called octahedral, and in octahedral we have 4 in one plane, then 5th one here and 6th one here. Examples are SF6. Okay, let us revise it once again. If 2 electron pairs or 2 bonds are there, then it is a linear. 3 trigonal planar, 4th tetrahedral, 5th trigonal bipyramidal, and 6th is octahedral. Here this is without any lone pairs. Okay, now we will see with lone pair how the distortion takes place and how the bond angle changes. So that is the first one. That is, we can start with like 3, there should be total 3 electron pairs. Okay, number of electron pairs is 3. In that 2 is bonding and 1 is lone pair. Okay, 3 total electron pairs are 3. 2 electron pairs are involved in bond, and 1 electron pair is lone pair. Okay, under getting this one. So this one will be like this. So there are 2 bond pairs. So if you have, I'll explain here. Just see. If you have 3 bond pairs, okay, then the shape was like this: A, B, B, and B. Right, this is trigonal planar. Now what happens, there is no 3 bond pair, we have 2 bond pairs plus 1 lone pair. Okay, so here what happens, okay, so this is just a now lone pair. Okay, now that is why there will be repulsion here, there will be repulsion here, and these two things will come more closer. And the if you see the arrangement, it is still trigonal planar, but the shape actually is bent. When we talk about shape, okay, when we talk about shape, the lone pair, okay, I'll write lone pair is neglected. Okay, so if I see for this one, it will be A, B, and B, right? So you can see this is a bent molecule. Okay, it's a bent shape, so that is why the name is bent. The example here is your you can write SO2 or O3. Okay, SO2 or O3. So I can write like this: SO2 or O3. Okay, now next one, if you see, you have okay, next you have total 4 electron pairs. Okay, we have 4 electron pairs. Okay, then here also we have 4 electron pairs. If it is there, then it is tetrahedral. If you remember A, then we have 4 B's like this. Okay, so this is your tetrahedral geometry. Now if there is 4 electron pairs, it can be in the form of 3 electron pairs and 1 lone pair. Okay, 3 electron pairs or 3 bond pairs and 1 lone pair. If it is 3 bond pairs and lone pair, the electron geometry is still tetrahedral, but shape you will ignore this one, right? For shape you need to ignore the lone pair. Okay, so how will it be looking like? This is just like this. Okay, and this one is called as trigonal pyramidal. Trigonal pyramidal example is NH3. Okay, now coming to the next one, that is your 4 electron pairs. It is like 2 bond pairs and 2 lone pairs. Okay, 2 bond pairs and 2 lone pairs. Okay, now if you have 2 bond pairs and 2 lone pair, here also what we can do, we can like ignore this one. So electrical geometry is still tetrahedral, but if 2 bond pair, 2 lone pair is there, the shape is like this: A, B, B, and we have 2 lone pairs here. So again, this is a bent shape, right? So angle here it is 1 H2O. Okay, so if you remember, the bond angle of tetrahedral, normal tetrahedral without any distortion, was 109 degree. In NH3, due to this distortion, it is 104 degree, and here, sorry, 7 degree, and here it is 104 degree. Okay, next coming to, if we have 5 electron pairs. Okay, now these 5 electron pairs can be in the form of 4 bond pairs and 1 lone pair. 4 bond pair and 1 lone pair. Okay, so if you have normal 5 electron pairs, then the shape is like this, right? So you have A, B, you have like trigonal plane, it is like this. So if you have 5 bond pairs, then it is like A, then you have 3 B's in one plane, we have discussed, 1 B at this plane and 1 this at this plane, right? Now what we are having? We are having 1 lone pair, right? So there will be 4 bond pairs, and this one is converted to lone pair. Okay, so now this is called, the electrical geometry is still trigonal bipyramidal, because we are considering the electrons, but when we consider shape, we need to forget the lone pair, right? So we will have just like this: A, B, B, and B and here one B, right? So you can see if you just turn it, okay, it looks like a seesaw, okay, that is why the shape is called as seesaw shape and the example is SF4. So you need to remember the examples of each type of geometry, you need to remember it because questions will be asked from here definitely, okay. Next, coming to if we have three bond pairs and 2 lone pairs, okay. In the same geometry we have 3 bond pairs and 2 lone pairs. It is like this: A, you have B, B and B, just like this. There is no lone pair is not shown here. So if you see, this is a T-shaped molecule and the example here is ClF3, okay. Next, if we go to 6 electron pair, okay. Now 6 electron pair was actually octahedral, right? The electron geometry is octahedral. But now if you have 5 bond pair and 1 lone pair, okay, this is like this 5 bond pair. So actually it should be, if there is no lone pair, then it is like this: 1, 2, 3, 4, 5 and 6, right? So you have here 4 bond pairs, 5 bond pairs and there's 1 lone pair, then we call it square pyramidal, okay, square pyramid, and the shape here is BRF5, BRF5, okay. Now coming to same, if you have 4 bond pairs and 2 lone pairs, okay, 4 bond pairs and 2 lone pairs, so you will have like 4 bonds, 4 atoms are present in one plane and 2 lone pairs are present here, okay. Now this is, the shape will look like this, shape will be like this, and this is called square planar shape, that is XeF4, okay. So these are the different examples that you should remember, clear? So with this, the VESPR theory is completed. Now we will go to Valence Bond Theory, okay, very important thing you need to understand. See, Valence Bond Theory says that whenever 2 atoms form a bond, okay, their valence orbital or their outer orbitals overlap with each other and there is a bond formation, okay. So you can see here, when 2 atoms come closer to each other, partial merging of the atomic orbitals takes place and this is called as overlapping of atomic orbitals, okay, overlapping of atomic orbitals, which results in the pairing of electrons, okay. Due to this overlapping of electrons, there is pairing of electrons of opposite spin and a bond is formed. Now, the extent of overlap decides the strength of a covalent bond. If there is greater overlapping, there will be more stronger bond. If it is poor overlapping, then it is a weak bond, okay. So in general, greater the overlap, stronger is the bond. Now next important point, now see, therefore according to the orbital overlap concept, that is when 2 atoms come closer, their valence orbitals overlap with each other. So based on this concept, the formation of a covalent bond between 2 atoms result by pairing of electrons present in the valence shell having opposite spins, okay. So orbital overlap concept is clear. According to valence orbital theory, 2 atoms which want to form bond, they come closer to each other and their valence orbitals overlap with each other. The electrons of 2 opposite spin come together and that is where a bond is formed, okay. So this is all about orbital overlap concept. Now we will go to the second thing, that is overlapping of atomic orbitals. Now see, when orbitals of 2 atoms come close to form bond, their overlap may be positive, negative or 0 depending on the sign or phase and direction of the orientation of amplitude of orbital wave function in space. Now let me first tell you, when 2 atoms are coming closer, their orbitals will overlap, okay, and these overlapping can be positive, negative or 0. Now before understanding what is positive, negative and 0, let us have a look at the shape of the different orbitals, okay. So if I want to give you the shape of the orbital, so S orbital, okay, is spherical shape, P orbital is plus minus shape, okay. These 2 things you should remember, okay. S orbital is spherical shape and we write only one sign here, and in P orbital it is plus and minus, okay. The P orbital, you know, 3 types, Px, Py and Pz, so you can just change its direction. It is Py and then you have Pz, okay. So yes, these are the shape of the orbitals, okay. Now we will go and learn about the positive, negative and 0 overlapping. So now you can see here, Px, Pz is overlapping, okay. So if the positive sides of one pz and the positive of another pz will overlap, then it is called positive overlap. Or the negative of one and the negative of another can also overlap. Same sign should overlap, then we call it positive overlap. Okay, so you can see pz positive overlapping is there, and pz negative overlapping means you can see the first pz plus is taken and second pz negative is taken. So this is called as negative or out of phase overlap. When same sign will overlap, it is positive or in phase overlap, and if opposite signs will overlap, it is called negative or out phase overlap. Okay, so do not think that positive means it can only positive can overlap. Even the negatives can also overlap. So remember, positive overlap means same sign, negative overlap means opposite sign. Okay, now if you see here, pz and s is always positive, so plus and plus, this will be a positive overlap. But if you see here, s is always positive, pz is negative part if it is overlapping, then it is called negative overlap. Now if we have px, okay, so px, suppose it is taken in the what we say vertical manner. So if this plus and minus, two p orbitals are there, okay, one is two p orbitals overlapping like this. P orbitals can also overlap like this. So if positive, negative is overlapping, then it is called positive overlap here. But if positive negative and negative positive is overlapping, then it is out phase overlapping. Okay, so we have sent two pz, one pz and px, and then pz and s, then we have two px. Next you can see two py also. Py can have positive overlapping and negative overlapping as well. Okay, so which are orbitals can overlap? First is your pz. Okay, pz overlapping can be positive, negative. Next pz and s. Okay, next you have px and next you have py. Okay, now we will see what is zero overlapping. Zero overlapping means those orbitals which cannot overlap at all. Okay, so there are two cases of that. One is your px means any vertical p, generally px and py with s orbital, there is zero overlapping here. Okay, there is no good overlapping between them. Here plus is there, here minus is there, so it cannot overlap. Similarly, two, that is px and py, their shape is like this, right? There one is vertical and one is tilted, so they also cannot overlap. Okay, so what are the zero overlappings? We have zero overlapping is with px or py and s, and we have px and py. Clear? So this is the overlapping of atomic orbitals. Third, now we will see types of overlapping. Okay, so type of overlapping and the nature of covalent bond. So if there is head-on overlapping, okay, head-on overlapping, we get sigma bond. Head-on overlapping means direct, face to face there is overlapping, then we call head to head or face to face overlapping is there, then sigma bond is formed. Okay, sigma bond is formed by head-on overlapping. Now what all overlapping can give you sigma bond? Now see, just in the last slide we saw what are the different types of orbital, different types of overlapping. So I will list down here. Here you see we have head-on overlapping are pz, s and pz, right? This is not what else? This is not head-on, this is from lateral, from side, not face to face. Okay, they should be face to face overlapping. So this is not there, this is not there. Another can be ss. Okay, two s orbital can also undergo head-on overlapping. So that is what is given. So whenever there is head-on overlapping, we have sigma bond. That type of bond formed is called sigma bond, and this head-on overlapping can be done by these three characters or these three orbitals, ss, sp and pz. Okay, generally it is pz. So you can see here, when two s orbital will combine, it will be like this head-on. Then you have one s and one p. So if you see here, we have the shape that this one should be positive, this one should be positive, and this one is negative. Next you have two pp, that is positive, negative and negative. Okay, so these three types of overlapping will give you sigma bond, or that is called, these three types of head-on overlapping will give you sigma bond. Okay, now coming to what is pi bond. So we have seen that there were another type of overlapping which took place laterally. Okay, so these two, px and py, this will give you pi bond. Okay, so that is not head-on overlapping, this is sidewise overlap. From the side they are overlapping, okay, not head to head. Clear? So in that case we have, this can be either px or it can be py. Okay, so py or px will give you, again we have seen px and py can overlap positive or negative. So if this is plus plus, this is minus minus, we'll get like this. If this is plus, this is minus, then we get like this. Okay, negative. So this is your positive overlap and this is negative overlap. Getting? Okay, so now we will talk about the strength of the bonds. Okay, now see, generally whenever there is head-on overlapping, so we just discussed in the starting that wherever overlapping is very good, when the atomic orbitals can overlap better, the bond will be stronger. Okay, so in sigma bond there is better overlapping, so sigma bonds are definitely stronger than pi bonds. Okay, so you can see in case of sigma bonds, the overlapping of orbitals takes place to a larger extent, so hence it is stronger as compared to the pi bond, where the extent of overlapping occurs to a smaller extent. Okay, here I want to add one more point, that pi bond is formed after sigma bond. Okay, means two atoms, suppose A and B is there, they will not form pi bond first. Always there is a formation of sigma bond. After that, if required, there is a formation of pi bond. Okay, clear? Fine. Now we will go to the next topic, that is hybridization. Now what is hybridization? Very simple concept. I'll give a very simple example. See, what happened? A teacher was there, I am there, and two of you came to me. Okay, and I had two laddus with me. Okay, one laddu was made up of bundi, okay, and another laddu was made up of dry fruits. Okay, one bundi laddu and one dry fruits laddu. Now I have only two. Okay, but you people like both want one type, you both want dry fruit laddu, no one wants bundi laddu, but I have only one, how can I give? And you don't want half also, you need one full laddu. So what I did is, I am a teacher, I will be very more like much more cunning than you, right? What I did, I mixed both of them. Okay, I mixed both of them, two laddus I broke them, I mixed both of them, and then I prepared two new laddus. Okay, now this laddu has the character of both bundi and dry fruits, and this laddu also has the characteristics of both bundi and dry fruits. Now you cannot say I don't want, you are getting dry fruits in both the laddus, right? So now I'll be giving you two laddus, and both of you got dry fruits, so both of you are now happy. Okay, so now what is hybridization is the same concept. Now in hybridization, what happens? The atomic orbitals, the valence atomic orbitals first undergo a hybridization. First they undergo intermixing, and once they undergo intermixing, they form now new orbitals, that is called as hybrid orbitals. So see, individually suppose I had one bundi laddu and one dry fruit laddu, 2s and 2p. Now 2s and 2p mixed, the two laddus mixed, and then two new laddus are formed, which has the characteristics of both bundi and dry fruits, and that's why it will have the characteristics of both s and p orbitals. Clear? Let us see this one. So hybridization is intermixing of orbitals of similar energies to form a new set of orbitals of equivalent energies and shape. So when I made two more new laddus, their shape, their size, their mass, which everything is same, but now it has the characteristics of both bundi and dry fruit laddu. Getting? Same thing. Now you will understand some features of hybridization. Okay, the first one is number of hybrid orbitals equal to number of atomic orbitals that get hybridized. Suppose 2s and one 2p orbital has undergone hybridization, then two atomic orbitals have undergone hybridization. After hybridization, two new hybrid orbitals will form. So the number of new hybrid orbitals formed will depend or is equal to the number of atomic orbitals that has undergone mixing. Okay, now second thing is equivalent in shape and energy. So the two laddus that I gave you finally, they should be equal. So the two hybrid orbitals that we get finally should be equivalent in terms of energy and shape. Next, directed in space to reduce the repulsions and can indicate the geometry of the molecule. So based on hybridization, we can tell the geometry of the molecule. Okay, very easily we can tell the geometry of the molecule. Clear? So now let us see the hybridization, types of hybridization. Okay, the first type of hybridization is sp hybridization. So in sp hybridization, what happens? See, in sp hybridization, one s and one p, especially generally pz, okay, orbitals, so it's not like 1s and 1p, I will write like ONE1. Okay, in number I am telling 1 s orbital plus 1 pz orbital combines. So 2 orbitals are combining, so what I will get when they combine, I will get 2, or I will write again this one in number 2 spz orbitals. Okay, I will get 2 spz orbitals, and the symbol of this one is like this. Whenever you have sp hybrid orbital, we show up one big lobe and one small lobe, spz, or you can just write down sp. Okay, no need to mention z, just sp. Okay, so now in this what happens, so total if there is 100% in this orbital, we have 50% S character and 50% P character. Okay, so the two laddus if I mix there, in each laddu you will get 50% will be dry fruits, 50% will be bundi. Similarly, in the other laddu will also be having 50% dry fruit and 50% bundi, right? Same thing here, clear? So next we will see what will be the shape of SP. I told you the last point, hybridization can tell you about the shape of the molecule. So if there is SP hybridization, then the molecule shape will be linear. Okay, if it is a linear shape, bond angle is 180 degree. Examples are BeCl2 and C2H2. Okay, now let us see these examples. So wait, okay, here you can see 1s and 1p has BeCl2, right? So let us understand this one. This is what? This is s orbital and this is p orbital. Okay, so if you write the electronic configuration of beryllium, so it is 1s2 and 2s2, right? So what happens here? Okay, beryllium, hydrogen, helium, lithium, beryllium. Yes, 1s2, 2s2, and after that there will be 2p orbitals as well, right? So now this 2s and 2p orbital of beryllium, this is 2s and this is 2p. Okay, now this 2s and 2p orbital of beryllium will undergo hybridization to give you hybrid orbitals. And what is this hybrid orbitals? sp hybrid orbitals. How many sp hybrid orbitals have formed? Two sp hybrid orbitals is formed. So you can see now this beryllium, this is one hybrid orbital and this is another hybrid orbital. Okay, now what will happen? So now beryllium is ready to form bonds with chlorine. So chlorine will come, its p orbital is there. So chlorine is not undergoing hybridization. The central atom will undergo hybridization. Okay, so this one will undergo hybridization and chlorine is there with its p orbital to form bond with hybrid orbitals of beryllium. Okay, so now you can see the structure of beryllium is like this. You have Be, Cl and Cl. So you can see this angle is 180 degree. Okay, clear? Next, if we see another example is your ethyne molecule. Okay, ethyne molecule, that is your sp hybridization. So if you see for ethyne molecule, let me explain here. Okay, now see, carbon is having electronic configuration of 1s2, 2s2 and 2p2. Right? Now if you see ethyne molecule has like this structure, right? So this hybrid orbitals will only form sigma bond. Okay, hybrid orbitals can only form sigma bond. So if you see this carbon, okay, it is forming one sigma bond and here one sigma bond, right? Two sigma bonds are formed. So now what happens? But in total it is forming 4 bonds, so we need 4 unpaired electrons in carbon, right? But we have now currently only what? So if I draw the valence electron, 2s is like this, okay, and we have 2p, okay, 2p, 2 is like this and 2s is like this. But carbon has to form, each carbon has to form total 1, 2, 3 and 4 bonds, so we need 4 unpaired electrons. So that is why what happens here, this 2s1 electron goes to 2p. Okay, so we get like this 2s and 2p. Now these are 4 unpaired electrons of 2s and 2p. Now one s orbital and one p orbital. Okay, one s orbital and one p orbital will undergo hybridization to give you 2 sp hybrid orbitals. So now this carbon is having two sp hybrid orbitals. One is, you can see this red color and this red color. Similarly, this carbon will also have two sp hybrid orbitals. So this sp and this sp. So now this carbon-carbon hydrogen bond is formed, carbon-carbon bond is formed, here carbon-hydrogen bond is formed, here carbon-hydrogen is formed. Now if you see, this two has undergone hybridization. There is two p orbitals which are not hybridized, so that is this green color p orbitals. Okay, so this carbon is having two p orbitals, similarly this carbon is having two p orbitals which form bonds, but they are undergoing lateral hybridization, so that is why this is pi bond. Okay, once again I am explaining you, listen here clearly. See, carbon, okay, carbon electronic configuration is 1s2, 2s2 and 2p2. Okay, ethyne, if you see, C2H2 structure is like this. Okay, so each carbon is having two sigma bonds. Okay, the first bond is sigma, the other bonds are pi bonds, two sigma bonds. Okay, now what happens? So, but each in total carbon is forming four bonds, right? 1, 2, 3 and 4. 3 with carbon, another one is with hydrogen. So it is forming 4 bonds, means we need 4 unpaired electrons in the valence shell. So I can write carbon electronic configuration like this: 1s2, 2s, if you see it is like this, 2s2 and 2p2. Okay. So now what happens? One of this get excited to the outermost electron. Okay. So this one gets excited to here. Okay, so that we get 4 unpaired electrons and 4 bonds can be formed. Now if you see, this s orbital and p orbital undergo hybridization. Okay, so they will form sp hybrid orbital. Now how many sp hybrid orbital will form? 2 sp hybrid orbital will form for each carbon. Why? Because two atomic orbitals are combining. The first rule, if you remember, number of hybrid orbitals is equal to the number of atomic orbitals combined, right? So s and p orbitals have combined, we got 2 hybrid orbitals, and for each carbon the same thing will happen. So you can see this is one hybrid orbital of carbon, this is another hybrid orbital of carbon. Similarly, this is one hybrid orbital, this is another hybrid orbital. So now you can see here this hybrid orbitals can form only sigma bonds. So this hybrid orbital and this hybrid orbital formed one sigma bond, and this hybrid orbital and this hybrid orbital formed another sigma bond with the hydrogen. Now but we need total 4 bonds, right? Each carbon is having 4 bonds. So the rest 2 bonds, so already 2 is done. The rest 2 bonds are done by this not hybrid or unhybridized p orbitals, that is your this one and this one, which is forming pi bonds. Okay, so that is the shape of ethyne molecule. Okay, now coming to the next hybridization, that is sp2 hybridization. So here the shape is trigonal planar, angle is 120° bond angle, and example is BCl3 and C2H4. Now if you see BCl3, what is the electronic configuration here? 1s2, 2s2 and 2p1. Okay, now what happens? If you see, s is having 2 and we have here p1. Now what happens? One of the electrons, see, if you see the structure of BCl3, okay, BCl3 if I draw, it has to form 3 bonds, right? So we need 3 unpaired electron. So that is why what happens, this one moves here and we get this one moves here and we get 3 unpaired electrons. Okay, now what happens? This is s orbital and this is p orbital, right? These 3p, 1s and 3p orbitals will undergo overlapping or hybridization to give you sp2 hybrid orbitals. What is the name of the hybrid orbitals? sp2. How many such sp2 orbitals will form? 3, because 3 orbitals have combined, right? So now if you see boron, okay, if you see boron, okay, boron is having now 3 sp2 hybrid orbitals. Okay, these are all what? sp2 hybrid orbital, sp2 hybrid orbital and sp2 hybrid orbital. Okay, boron is clear. Now if you see about chlorine, so chlorine will come and form bond with, so chlorine is having unhybridized p orbital, so that will form bond with chlorine. So you can see here, this is given, boron is having 3 sp2 hybrid, each one name is sp2, right? sp2, 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 then it is forming bond with chlorine, chlorine and chlorine. Okay, so this shape is called as trigonal planar and this bond angle is 120°. Clear? Okay, now there is another example also from sp2 hybrid orbitals or sp2 hybridization, that is your ethene molecule. Okay, so if you see, ethene molecule is also having sp2 hybridization. Now if we understand this in little detail, so if you see carbon, okay, so carbon electronic configuration is 1s2, 2s2 and 2p2, right? So I can draw like this, 2s2 and 2p2. But now if you see ethene molecule, it is like this. So this one is forming 3 sigma bonds, so we need 3 unpaired electrons. So that is why what happens, for getting 3 unpaired electrons, what we can do is we can excite one of the electrons to here. Okay, but how many sigma bonds are required? We have only 3 sigma bonds, so 3 atomic orbitals can combine. So we have one 2s orbital and 2 2p orbitals to combine or to undergo hybridization. So now these total, so after hybridization we get here 3 sp2 hybrid orbitals. We get 3 sp2 hybrid orbitals. So now if you see, carbon has one sp2 orbital here, this is one sp2 orbital and this is another sp2 orbital. Similarly, this carbon is also having 3 sp2 hybrid orbitals. Okay, now what happens, if there are 3 sp2 hybrid orbitals, one is used to form a sigma bond here, another is used to form a sigma bond with hydrogen, and another is used to form a sigma bond with hydrogen. Now there is one more unhybridized p orbital. Unhybridized p orbital of 2 carbons form a pi bond here. Okay, so and the bond angle, if you see, it is 120 degree. Okay, similarly we have another hybridization, that is sp3. In sp3 the bond shape is tetrahedral, bond angle is 109 degree. Okay, now how can we explain this? So if you see CH4 molecule, okay, now CH4 molecule, if you see carbon has 1s2, 2s2 and 2p2. CH4 structure is suppose like this. So how many bonds, how many sigma bonds it is forming? 4 sigma bonds, so we need 4 unpaired electron. So it is 1s2, 2s, I can draw like this, 2s and 2p, okay, 2p2, and this one electron comes here, right? Now this sp3 hybridization takes place. So what happens, 1, 2s and 3 2p orbitals will combine to give you 4 sp3 hybrid orbitals. Okay, 4 sp3 hybrid orbitals are formed. So now this carbon has 4 sp3 hybrid orbitals. Okay, now what happens after that? These 4 sp3 hybrid orbitals form bond with hydrogens. Okay, you can see the structure here to give you tetrahedral structure. Okay, now there is another molecule also, C2H6 can form bond like that. Okay, so I'll erase this to understand C2H6. So now if you see, C2H6 structure is like this. Okay, yes, I can draw like this, right? So carbon is having how many sigma bonds? 4 sigma bonds. So carbon is having 4 sp3 hybrid orbitals. Okay, now this one will form bond with hydrogens. Okay, so that, and this one will form, these are all what? sp3 hybrid orbitals. Okay, so here there is a sigma bond, these all are your sigma bond. So that you can see here. Okay, so okay, clear. Now coming to another example of this one, that is, I will add here 2 molecules, NH3 and H2O. Okay, here something different is there. NH3, if you see nitrogen electronic configuration, 1s2, 2s2 and 2p3, right? In NH3, nitrogen forms 3 bonds, right? So we need 3 unpaired electrons, and 2p3 is already having 3 unpaired electrons, right? So what happens now, if you see, this is the structure. Okay, now what happens, all these orbitals undergo hybridization to give you 4 sp3 hybrid orbitals. Now the question is arising like why only 2p, why 2s is forming hybridization or orbital, right? So here it is because you need like one, or these all are same energy, these all are degenerate orbitals are having same energy. It should combine with another molecule, it can mix with another molecule, right? Or not molecule, another orbital. So 2s and 2p will undergo hybridization to give you what? 4 sp3 hybrid orbital. So now nitrogen got 4 sp3 hybrid orbitals. Okay, now but the molecule is NH3, so we can use 3 of them to form bond with hydrogen. So these 3 is over. Now here what will be present? Here only nothing but this lone pair will be present. Now for this lone pair, what will happen? There will be repulsion here, because of which this one will get shrinked, and the bond angle here is not 109 but it changes to 107 degree. Similarly, you can see for water there will be 2 lone pairs and the bond angle here is 104 degree. Okay, clear? So okay, let us discuss the water in detail. So if you see oxygen electronic configuration, it is 1s2, 2s2 and 2p4, right? So we need like this 2s2 and we have 2p4. Okay, so now you see we need only 2 unpaired electrons in water because 2 bonds are only being formed, but everything will undergo hybridization. So oxygen has now 4 hybrid orbitals of sp3, 2 will form bond with hydrogen and 2 will contain the lone pair of electrons. Okay, clear this one, how it is coming? Okay, next we have hybridization involving d orbitals. Okay, so here you should remember that if the hybridization is dsp2, okay, then that is ds and 2p orbitals are there. Okay, then the shape is called as square planar. Okay, and the examples here are NiCN4 and PtCl4. These examples you will study in detail in class 12 chapter, that is your coordination compounds. Okay, next if it is sp3, okay, sp3d hybridization. So here how many atomic orbitals have combined? 4 atomic orbitals have combined. Here also 4 atomic orbitals have combined, right? This one is 5. Here it is 5. Sorry. 1 second. Okay. Yeah. So here 5 atomic orbitals have combined. So this is your trigonal pyramidal. Okay, trigonal bipyramidal. So here you will get example PF5 and PCl5. Next, if you have sp3d2, okay, sp3d2, then it is square pyramidal. Here you can get the example BRF5, and if you have sp3d2 or d2sp3, it can also be octahedral geometry, and you can get these as the examples. Okay, so these table you can remember the examples, but especially the first what we to discuss in detail are the where questions can be asked. Fine. Now let us see this hybridization of PCl5. Okay, so now if you see that phosphorus electronic configuration, if I just write down, okay, so yes, phosphorus is what? 3s2 and 3p3, right? This is the outer configuration. You have like this 3s2 and 3p3. Now see, phosphorus is forming 5 bonds, so we need 5 unpaired electrons, but now we have only 3 unpaired electrons. So what I can do is I can excite 1 electron here, right? So I can write it like this: 3s, 3p and 3d, and I have here 3s, I have 3p, and then we have 3d. 1, 2, 3. Okay, let me make it little bit smaller so that we can accommodate all the orbitals. So we have here 3s, then I have 3p, and then I have 3d. 1, 2, 3, 4, 2, 3, 4, 5. Yes, and here I have 3 and here I have 2. So now what I will do, okay, 1 electron I excited here. Okay, 1 electron I excited. Now what will happen? This one will give me s, p, 3 and d. These all orbitals will combine, s, 3, p and d. So how many combined, how many hybrid orbitals I will get? 1, 2, 3, 4, 5. 5 orbitals have combined, so I will get 5 hybrid orbitals. 5 sp3d orbitals I will get. So now this phosphorus you can see is having 5 sp3d orbitals. I can draw like this if it is, so 1, 2, 3, 4 and 5. These all are what? sp3d orbitals. Okay. Now each of these sp3 orbitals form bond with chlorine. Okay, clear? Similarly, you can see the example of SF6. Okay, SF6 hybridization, if you see, it is sp3d2. Sulfur electronic configuration is your 3s2 and 3p4, right? So you have like this 3s2 and you have 1, 2, 3 and 4, 3p4. Now what happens? We need 6 unpaired electron, but we have only 2, so 3d is there. So I can excite them 1, 2, 3, 4 and one more. 1 second, we can make it like this. Okay. We have 3s, then we have 3p and then we have 3d. 1, 2, 3, 4 and I need little more space here. Okay, 5. Okay. 1 second students, sorry for disturbance, but yes, I am not able to manage space here. So I have 3s, I have 3p and now I have 3d. Yes, 1, 2, 3, 4. Yes, now it is correct. 2 and here. So I have 3s2 and I have 3p4, right? But I need 6 unpaired electrons, so I will excite one electron to this one, right? So I will excite these electrons to here. These electrons have come here. Now this sp3d2 will undergo hybridization. So how many orbitals are there? 6 orbitals have undergone hybridization. So how many hybrid orbitals I'll get? I'll get 6 sp3d2 hybrid orbitals. Okay. Now if you see sulfur, okay, if you see sulfur, we have 1, 2, 3, 4, 5 and 6. Each of them has sp3d2 hybrid orbitals. Okay. Now what happens? These fluorine will come and form bonds with this one. Okay, clear? So you can see, and this shape 4 will be in one plane and 2, 1 up and 1 down, and this shape is nothing but octahedral. Clear? Okay. So that is all about hybridization and all. Now we are going to practice some questions from this particular topic. Many previous year questions are generally concentrated on this particular topic. Okay. So now first I will be discussing the homework question that I gave you. In NO3 minus ion, the number of bond pair and lone pair of electrons on nitrogen. So if you see nitrogen, okay, valence electron is 5. Oxygen is like 6 into 3, 18, and there is 1 positive charge, so 1 negative charge. So total we have 18, 24 electrons we have, right? So total valence electron is 24. Okay, I need to arrange this 24 electrons in this one. So I have nitrogen, oxygen, oxygen. Okay, so what I'll do? I'll give 1 bond, 2 bond here, this bond here and this bond here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, total I have to use 24, 8. Now 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 and 23, 24. So yes, all the octets have been satisfied. Now the question is number of bond pairs. So around nitrogen we have 1, 2, 3, 4. 4 bond pairs, and there is lone pair, no lone pair. So 4 and 0, that is option number D here. Okay. Next, the percentage of S character in the hybrid orbitals of nitrogen in these compounds are given. Okay, percentage of S character you have to see. So first, if you see structure number A, that is NO2 plus, we have NO2 plus, right? So nitrogen has 5 valence electron, oxygen has 6 valence electron, right? So I have 5 plus 6 plus 6 and then I have minus 1. Okay, because we have 1 positive charge. So 6 plus 6, 12 plus 5, 17, 17 minus 1 is 16 valence electron. Clear? We have here 16 valence electrons. We need to arrange that. So now if I write nitrogen, oxygen and oxygen, 16 valence electron I need to arrange. So 1, 2, 3, 4. Okay, 1, 2, 3, 4. Then I can write 5, 6, 7, 8. Okay. Now 9, 10, 11, 12, 13, 14, 15, 16. Yes, 16 valence and all the octets have been also satisfied here, right? So now if I see hybridization here, okay, so what can be the hybridization? If you see here we have 1 sigma bond and 1 sigma bond. So just remember here, if you have 3 sigma bonds, then hybridization should be sp2. If you have 2 sigma bonds, hybridization is sp, and if you have 4 sigma bonds, then hybridization is sp3. right? So now if you see there are 2 sigma bonds, if 2 sigma bonds means hybridization has to be sp. If there is total 100%, s will be 50%, p will be 50%. So s character 50% for the first one. So that is your option number B is the correct answer. But we will see for NO3 minus also now. Okay, so I will erase this one. Okay, option number B is NO3 minus. Okay, just now we did the structure of NO3 minus. If you remember, it was like this, right? 1 2 3 4 5 6 1 2 3 4 5 6 1 2 3 4. So beside nitrogen there is 1 sigma bond, 1 sigma bond, 1 sigma bond. This is pi bond, right? Only 1 sigma bond can be present between 2 atoms. The rest of the bonds will be pi bond. So if it is 3 sigma bond, it has to be sp2 hybridization. So now if sp2, if it is 100%, so each one will be 100 divided by 3, 33.3, and here 33.3, and here 33.3. Right? So that means the next one will be 33.3%. Now next one, if we see NH4 plus. So NH4 plus, if you calculate total 5 here and 4 here minus 1, so 5 plus 4 9 minus 1 8 electrons are there. So I can just draw 4, okay, 4 hydrogen, 1 2 3 4 5 6 7 8. 8 electrons are present. If 8 electrons are present, then it will give you this is all the valence electrons are used. So 4 sigma bonds are there. 4 sigma bond is sp3 hybridization. Now you can divide it into 4 parts. 3 parts will be p and s will be 25%. Option number B here. Okay. Next question number 2. Bond length in pH4 plus is more, bond angle in pH4 plus is more than that of pH3. So if you see, pH3 structure is like this. Okay. And pH4 structure is like this. Now this is a pure tetrahedral, there is no lone pair, so there will be no repulsion, and this angle will be 109. But here there is repulsion, okay, so that is why there will be some angle less than your 109. So that is because of lone pair. So what is the reason here? pH4 has square planar structure? No. pH3 has planar trigonal structure? No. Hybridization of P changes when pH3 is converted to pH4. Yes, hybridization is changes. Lone pair, bond pair, repulsion exist in pH3. Yes, this is the reason why the angle has changed. That is option number D. Okay. Next, okay, here this hybridization of P does not change, right? Here also it is sp3 and here also it is sp3. Okay, but here that is 3 bond pairs and 1 lone pair, and here it is 4 bond pairs. Yeah, that is the difference. Okay, next, the state of hybrid orbitals of carbon in CO2, CH4 and CO3 2-. So this question was asked in 2018. So if you see, CO2 structure is like this, right? Now here we have only 2 sigma bonds. If 2 sigma bonds, then hybridization will be sp. So you can see only one option with sp, option number C. CH4, if you see, the structure is like this, CH4. Okay. So here we have 4 sigma bonds. 4 sigma bonds will have sp3 hybridization. Then we have CO3 2-. Okay, CO3 2-, sigma sigma sigma. 3 sigma bonds, so that is sp2 hybridization. So sp, sp3 and sp2, option number C here. Next, question number 4. The hybridization of C in diamond, graphite and ethine are in the order of. Okay. So if you remember, diamond, in diamond the carbon has tetrahedral structure, so it is sp3 hybridization, and then so we can eliminate these 2 options. In graphite it is sp2 hybridization, and the last one ethine, it is sp hybridization, so option number B here. Next, the pair of compound having identical shapes for their molecule is, we need identical shape. Okay, so if you remember, CH4 is tetrahedral, SF4 is seesaw, right? So we can eliminate this one. If you see next one, BCl2, BCl2 will have bent shape, and ClF2, I have to remember, Cl has 7 electrons, right? Yes, and 2 is forming FF, ClF2. Okay, so is it linear shape, right? We have one, yeah, ClF2 is like this. This one will be linear. Okay, so that is why we can erase this one. So this is also not having same shape, right? Because BCl2 is a bent one. So we can eliminate this option. SO2 and CO2 is also, SO2 is bent, CO2 is linear, so that is also not there. So correct answer has to be option number C. Now you need to comment me down and tell me what is the shape of XeF2 and what is the shape of ZnCl2. Okay. Next, question number 6 is from your NCERT exemplar. Which of the following species has tetrahedral geometry? Okay, tetrahedral geometry means we need sp3 hybridization, okay, with no lone pair. Okay, now if you see NH2 minus, N has 6 electrons, 1, 2, 3, 4, 5 and 6, right, H2. So 2 bond pair and 2 lone pair, so this is bent shape. CO3 2 minus, it is trigonal planar. Whichever I know, I am not drawing it, you can remember or you can practice the structure again. H3O plus, so you have oxygen. Oxygen has 6 valence electron, but it is showing H3O plus, so I can calculate the total number of electrons. So here 3, here 6, 6 plus 3, 9 minus 1, that is 8, right? So you have 8 electrons, so I can draw like this 1, 2, 3, 4, 5, 6 and 7, 8, right? So this one again will be pyramidal, okay, because it is having one lone pair. Now if you see BH4 minus, so this is nothing but tetrahedral. So option number A is the correct answer here. Okay, next, number of pi bonds and sigma bonds in the following structure is, okay, so this question you can leave now, okay, I just forgot to add the structure, so but I'll just give you any random structure, okay, this one we will discuss this question in the next class, I'll do it again. For now we can leave this question because I haven't added the structure here. Okay, now this is a homework question. Which of the following angle corresponds to sp2 hybridization? Okay, very easy question. What is the bond angle for sp2 hybridization? You need to comment down the answer. Okay, so yes students, that was all about VBT, Valence Bond Theory, VSEPR Theory and hybridization. Okay, very important part. So please mug up, like learn the shapes of different molecules so that you can do these questions easily and quickly without wasting time in the exam. Okay, these questions are very I can say mark fetching, you can easily score them, just you need to remember the shapes correctly. Okay, that's all in this students. So thank you for watching and please subscribe the channel. Do not forget your target 60 out of 60 in KCET Chemistry. So yes students, and see you soon in the next class.